Dear students and participants on the course on railway engineering, with this lecture, we are coming towards the end of this module and as well as the end of all of the lectures which we have taken up and we thought of taking it up in this particular course. Today, we are going to talk about the high speed tracks. In the previous lecture, we completed the track renewals and the track renewals were discussed with respect to the points and crossings, and then some information was given regarding the TRT, that is the track renewal train. And then another important aspect related to the tracks, that is the drainage, was discussed in length, wherein we talked about the requirements, we talked about the drainage systems which needs to be provided between the stations, that means between the tracks, then at the station yards, at the platforms, and then finally the subsurface drainage methods which can be used if there is a problem of water accumulating in that area, creating a problem to the track. Today, we are going to specifically talk about the high speed tracks. The high speed tracks are the need of the today. As you know that as a nation, we are moving towards the provision of the tracks which can take up the movement of the trains which are moving at a speeds like 160 kilometers per hour, and tomorrow it can be 200 or 250 kilometers per hour. So, if these type of tracks needs to be provided, then we should know that what are the effects of those high speeds, and those effects of the high speeds will define that what type of modernization is to be done. And then once we talk about these type of aspects, then we will try to see that what are the various concepts which are usually used so as to attain super high speeds for the trains. And then some of the safety measures which are supposed to be taken will be discussed, and primarily these safety measures I am talking with respect to the measures which are already being adopted for this Mumbai Ahmedabad high speed rail corridor. Now, high speed tracks, these are the tracks which allow the operation of tracks for the speeds more than 120 kilometers per hour. If you remember when we discussed about the various types of tolerances or the criteria, there they were dependent on the speeds. They were dependent on the speed up to 50 kilometers per hour or 100, 110, 130, 160 kilometers per hour. So, in that light we can say it is around 120 to 130 kilometers per hour if we are going above that. So, it is falling towards the high speed. But then within that high speed there can be a normal high speed and a super high speed. Now, why it is required? Why we should now transform towards the high speed tracks? When we say high speed tracks here, it means we are talking about the tracks which can sustain the high speed movements. First thing is the rapidly increasing demand of the transportation. We need to take the people to the other side as fast as possible without having an issue with respect to the time which is being lost in the travel, because that is a productive time. Running heavy loads at faster speeds safely as well as economically. So, if you are moving at a very fast speed, then there may be an issue with respect to the track layouts, the geometric. So, the safety is a prime important factor here. So, need to take care of that. But at the same time, when we are doing it, obviously when you are going for a modernization, you are going for a higher requirements, that is going to cost. So, how economically that can be done is another aspect needs to be taken care. Better productivity. When you are connecting A with B in a very fast manner, say if you are talking about Ahmedabad and Mumbai, where the travel at the moment is taking somewhere around on an average of 6 or 7 hours. Now, if this high speed rail is started, those trains are started, it is going to take roughly 2 or 30 minutes to 3 hours. So, you are saving around 4-5 hours here, and that 4-5 hours will go into the productivity. Then better service to the customer, better social and economic development of an area. Obviously, when the things can be done at a much faster level, then people may not be hesitant to stay at Ahmedabad and work in Mumbai, because they are only 2 to 3 hours away. So, the area in Ahmedabad may start flourishing more. Or if you talk about the various stations which will be there on the way, around 10 stations are there. So, those stations are also going to develop, or when I say stations I am talking basically the area related to those stations. So, that development will come, and when this development comes it can be in both the forms, in the social form as well as in the economic form. Now, as I said, when you go into the high speed, there can be a normal high speeds where you are talking up to a speed of say 250 kilometers per hour, and there are speeds which can be about 250 kilometers per hour, which falls in the super high speed conditions. Now, when you have to achieve these things, when you have to go even to 250 kilometers per hour, there is a requirement of modernizing the tracks. The standards needs to be improved, they have to be taken at a higher level. Similarly, the control systems, the traction efforts, S and T systems which are provided so as to control the movement of the trains, they also needs to be improved upon it. So, new technologies needs to be embedded so that the safety can be ensured while maintaining the efficiency of the system. Now, what are the various effects of the high speed? Let us look at that. The track irregularities which are resulting in pitching, rolling, bouncing and lateral oscillations of the vehicle. So, any those parasitic movements, they will be there, because now you are talking about an x axis, you are talking about the movement on y axis, or you are talking the movement with respect to z axis. So, the movement is in the direction, or it can be in terms of the movement or rotation about that axis. Pressure and stresses, they will be there, and because of this then problems will get generated in the rolling stock, the rails which are being provided, the wheels which are running at the top of the rail. Now, why these are happening? There is a resonance effect. As soon as the wheel starts moving at the top of the rail and the speeds are getting higher, then there is a sort of resonance which will get induced between the two systems which are in contact. So, the resonance between the frequency of application of the load and the elastic oscillations of the track, and this may be at a certain location or this may be happening all along the track. So, this resonance is one big factor which limits the speed, and this also causes a problem with respect to the wear or failure of component. That means it also allows to research in the area of new materials. The new materials which can sustain the resonance which is being caused and does not cause negative impact in terms of the limitations on the speed or the failures of the component. The higher stresses due to the inertia or the springing action of the track is another issue which will be there. There are unbalanced weights, there are unspring masses. We discussed about these when we took the track resistances and the stresses. Suspension characteristics, and these suspension characteristics, they become more important when there is a say a movement on the curve. So, when there is a movement on the curve, so the body is moving in this form, there is a possibility, but because if we are going into a cant situation, then the way this suspension system is working so as to balance the loads. So, you may find that the suspension is going in this form. So, here there is a depression, whereas this remains in position as such, or it is getting elongated towards the top. So, those type of suspension characteristics will also induce the various types of parasitic movements. Wave formation. Now, one wave formation we discussed when we were talking about the creep, if you remember, and there we said that the wave can be formed in the rail and then can be carried forward, and that induces the creep. Now, here when you are having a very high speed, then you can understand the type of the wave which gets formed and gets carried, and then what is going to happen because of that is what we will be discussing. We will take this in a bit more detail. Then adhesion between the wheel and the rails when they are moving at a higher speeds. So at that particular speed, whether the rail and the wheel, they are having an adhesion with respect to each other or not, or they are getting loose in that sense. When they are getting loose, air cushion is coming at this location, then again there can be an issue with respect to the either overturning or sliding or slipping and all those. Then vibrational limitations. Vibrations are again correlated with the speed as well as with the track. The irregularities in the track, that the way the rails are being provided on both the sides, the gauge between the rails, whether it is tightened, it's slacked. So all of those things are also going to induce the vibrations. Then spatial problems on the curves, we just discussed about it. At the same time, the power requirement so as to generate that much effort or traction so that it can move at a higher speed, the train can move at a higher speed, and how it impacts about the track or the components of the tracks. So these few issues, that is wave formation, adhesion, vibration, curves and power requirements, we are going to take up in more detail. Now, propagation velocity of a wave in a medium sets the speed limit of a body moving in that medium. So, in whatever is the medium is there, in that particular medium, the propagation velocity is going to define that what should be the speed of a object which is moving in it. The higher speed, then the speed in the medium requires more power, because now whatever forces or whatever you can say that the resistances which are being induced due to that, you have to overcome that. In tracks, as the vehicle speed increases and approaches the velocity of the wave propagation in the rail, an extraordinary resistance comes into play. So that means now the two things are approaching the same, the vehicle speed and the velocity of the wave propagation. And at this particular point, when these two things are approaching to the same value, there are problems with the deflection of the rail. So this will be a problem in terms of a high speed and the stability of the vehicle. The wheel is accompanied by large amplitude of the stationary waves which can even destroy the rail. And this propagation velocity of the deflected wave of the rail seat sets a speed limit for the train. The research was done for that. It was done on a new Taikaido line in Japan. All the experiments were done with respect to different type of ratios which can be there. So this is the first one which we are talking, and it said that if you are looking at this velocity of the wave as well as the speed of the train, then the restriction will be up to 1800 kilometers per hour. That means we can go up to this particular limit. So it's a very high value. The similar phenomena exist between the pantograph and the overhead wires of the electrified railway. So when you talk about any of the vehicle which is moving, so here at the top it has a system by which it can take the power from the pole. So this pole has the system by which the power is given to the pantograph. So when you are talking about this, now when the speeds increases, now these two are interacting. Now when these two are interacting, the pantograph deflects the overhead wire at the point of contact, thus causing the wave formation in the pantograph or the overhead wire. And if the speed of the pantograph exceeds the propagation velocity in the transverse wave in the wire, the rapid growth of amplitude may destroy the overhead wire system. So this is another problem, this is another limiting condition. So one condition was with respect to the wheel and with respect to the rail here. Another condition is coming on the top. This transverse propagation of the velocity of wave in the overhead wire sets the speed limit. And again on the same line where the experiments were done, that is a new Taikaido line in Japan, this critical value has come out to be 400 kilometers per hour. So there is a drastic reduction from 1800 kilometers per hour which was there when we were talking about the resonance and the frequency and the propagation of wave in the rail and speed of the train. So, there that was 1800, but now it has reduced to 400 kilometers per hour. The speed can be increased by increasing the tension in the overhead wire or by developing a lighter wire material. But then again, for both of these things there is a limit up to what particular level the overhead wire can be given a tension. So, on the basis of the properties of that wire, there can be one point at which it will not be able to take further tension, and therefore, that becomes a limiting value there. On the basis of that, we can examine that up to how much value this speed can be increased from 400 kilometers per hour. Similarly, if you are talking about a lighter wire material, now this lighter wire material has an issue with respect to the conductivity. You cannot reduce the size of the wire. There cannot be a particular value below which then it will be a problem even in the handling, even in the way of working. So, considering these two aspects, again we need to see that up to how much level the increase can be given beyond 400 kilometers per hour. Another case is a adhesion between the wheels and the rails. Now, here the tractive force is working as a reaction of the rail due to the adhesion between the wheel and the rail. This adhesion tends to decrease with the increase in the speed. So, when we look at the graph which is given on the right hand side, this is a curve which is for the adhesion. So, as the speed is increasing, this adhesion is reducing, but the train resistance increases approximately with the square of the speed. So, we have discussed when we talked about the resistances. So, in some cases it was independent of the speed, in some cases it was dependent on the speed. So, it was proportional to V only, in some other cases it was proportional to V square. So, here this is a graph for the resistances. So, this graph goes in this form, it is increasing as the speed is increasing. Now, when these two graphs are taken, there is a point of intersection of these two graphs, and that point of intersection gives the speed at the bottom. So, the curve of adhesion curve between the wheel and the rail and the train resistances, they are plotted, and the two curves intersect each other at this particular intersection point. So, we are talking about the speed. If additional torque is applied above the speed related to the point of intersection, then the wheels slip on the rail and the torque cannot be utilized for accelerating the train because there is a slip. That means now this torque is got wasted. The point of intersection is limiting the speed, and this has been observed as 370 kilometers per hour under the worst condition. So, now we are further coming down. We started 1800, then in the next criteria we came to 400, now we are coming to 370 kilometers per hour. Now, if you have to increase this speed from 370 kilometers per hour, what are the possibilities? One is you reduce the train resistances. So, when you reduce the train resistances and if it cuts at some longer distance, obviously you are going to get a higher speed here. So, innovative techniques like use of linear induction motor, jet propulsion, etc., can be used so as to reduce these train resistances, and these are actually used when we try to go for the super high speeds. Then raising the adhesion between the rail and the wheels, this required the development of the new materials which are superior to steel. Now, talking about the vibrations, the track irregularities, they cause the vibrations, and as the speed increases, the vibration also increases, and then they get propagated. They get propagated along the length of the track as well as they get propagated towards the side in the transverse direction. Now, there are unstable self-excited vibrations in the rail vehicle even if the rail is geometrically straight. That means it is going very straight on the section, there is no issues. Even in that case also there are some self-excited vibrations, and this phenomena is known as hunting. Even after taking measures to reduce the track irregularities and improving the car body suspension, the speed cannot be increased to a very high value because of these vibrations, and this has been observed to getting limited to a value of 350 kilometers per hour. So, previously in the previous criteria we talked about 370. So, a bit of a reduction here. Now, if you have to increase upon this particular speed, then what we need to do is we need to float the train little above the surface of the track or the rail tabletop. So, that means sort of a air cushioned vehicle is what we are talking. So, the train is not touching the track when it is in the speed. So, there is a air cushion in between. In the case of curved tracks, obviously the problems are there. There is an unequal load which can come on the inner and outer rails, and when this comes on the inner and outer rails and there is a possibility of say the overturning or any other issue can be there, this is usually balanced by the provision of a super elevation. So, we just super elevate the track, and then on the basis of that the effect of the centrifugal force which may be there, which is causing these type of issues in terms of the unbalanced weights, is being taken care of. But then what is the limit up to which we can increase? Can we increase it like this? So, there is a limit up to which we can go in the increasing of the cant, and this is also going to limit the speed, because super elevation or cant, this is correlated with the speed. But at the same time, if you are going in this form, then there is a problem of comfort to the passengers. There is always a possibility of the sliding of the vehicle towards the inner side. So, the adhesion is going to be lost more in this particular case. So, there is a limit up to which you can go. Maybe we will not be able to go up to this, but we can go up to this particular value, and that value needs to be identified. So, the experiments were done again on the same line, that is New Tokaido line in Japan, and it gave the value of maximum lateral acceleration of 0.05 centimeter per second square, and that resulted in a cant value of 180 mm. So, at this particular criteria there was not much of the discomfort to the passengers. So, if we use this 180 mm cant and say if we use the radius as 2000 meters, it comes out to be a balancing speed of 200 kilometers per hour. That means if we increase the radius now further, now this particular speed can be increased. So, if we go to 3000 meters, it is going to be increased further, but we cannot increase the cant value because this is the limiting value and we should not change that. So, the modernization of the track is to be done. So, what are the things which needs to be taken care of? Use of the better designed rolling stock, use of higher standards of the track components, better telecommunication and signaling systems and their standards and specifications, use of modern techniques for inspection as well as for maintenance. So, some of the things we are taking up here, like the electric traction with higher power is one way of doing it. Heavy rail sections can be utilized where there is a more wear resistance, use of SEJs with LWRs and CWRs, use of PSC sleepers, higher sleeper density per kilometer, maybe more than 1660. Ballast sections as being talked about in LWR or CWR, elastic fastenings can be used, integrated track assemblies shall be used. Then in the case of turnouts, the crossing more than 1 in 16 is better. If we talk about this Mumbai Ahmedabad high speed rail, there it is being used as 1 in 18. Then higher cant deficiency, so it is dependent on the actual cant, on the permissible values of the deficiency which are there. Use of the cast manganese steel rails at the crossings and the curved switches. Using of the USFD ultrasonic flaw detectors so as to check the flaws in the rails before they are being used in the track. So, some of the track geometrics are being shown here for a permissible speed of up to 160 kilometers per hour, and say if the degree of the curve is changing. So, if it is only half a degree, then the radius can be 3492. So, for that equilibrium count, proposed count efficiency, on the basis of that the transition curve length are being given. But as it increases to 1 and 1 by 4 degrees, then this transition curve length increases to 180 meters, though the radius reduces here to 1395, because this degree of the curve and the radius, they are correlated by a formula. Then strengthened formation as per the requirements, the formation also needs to have more strength. So, we have talked about various of the things previously, some of the things are just writing here again. Providing topping layers with or without the waterproofing membrane, using subbulla piles, cement grouting at the locations where there is water pockets or ballast pockets, lime treatment, providing the subbank or the flattening of the slopes, or the increase in the depth of the ballast. These are few of the measures which can be taken up so as to strengthen the formation level. Another important aspect is the type of the traction which is required. Now, this traction can be talked in terms of the specific power. This is defined as the power which is required to move 1 tons of the passenger rolling stock, and it is correlated with the different type of resistances, speeds and accelerations. It is observed that with an increase in the speed, the requirement of power to overcome the resistances and to accelerate the train goes up very steeply. So, as you can see in the diagram which is being given on the right hand side, for the different values of f and different values of g, as the speed is increasing on the x axis, the specific power requirement in kilowatts is increasing. So, it is going in exponentially up. The test indicated that the speed of 300 kilometers per hour, the air resistance takes about 95% of the traction power, and 5% is taken by the suspension and the guidance system, that is the things which are being provided below the vehicle in terms of track or its own components. Now, one thing which is to be done is to have a GIT, that is a general inspection train, and this general inspection train has a number of wagons or cars, and these wagons or cars, they are equipped with the equipment which are required for the inspection, which are required to measure the various types of parameters which are related to the track, which we discussed in the case of track maintenance. We talked about the tilt, twist, we talked about gauge, we talked about alignment, we talked about the unevenness on the rails left and right. So, those things along with the accelerations in the vertical and the lateral directions, the power supply, the signaling, telecommunication systems, all of these things, with respect to all of these things, the equipment is available on this train, and then it can be used for the inspection. And this train, it can go up to a speed of 320 kilometers per hour, so as to identify that at this particular speed is any of the component of the track is not behaving in the correct manner. Just look at the super high speed concepts here. One is the linear induction motor. It helps in attaining very high speeds. The thrust is produced without physical contact, and therefore it can be used with any type of guidance system. It is free from adhesion and can take a speed up to 350 kilometers per hour. The another is the linear motor and air cushion system, and this combination can go up to a speed of 500 kilometers per hour. So, this is a air cushion system with a tracked conditions. So, gas turbine and air cushion or jet propulsion is another way of doing it. So, this tracked air cushioned vehicle, which is being shown here in this photograph, where the acceleration goes with the aero propulsion, that is 200 kilometers per hour in 2.5 minutes. So, it can attain that particular speed. If it is going with the linear induction motor, propulsion system and core gas thrust, then it can attain a speed of 380 kilometers per hour in 1 and 1 by 4 minutes if only a single motor is being used. And if the two motors are used, then it can go to a speed of 480 kilometers per hour in the same time. Then braking distance requirements, because if you are moving at such a high speed, then you have to brake it if this you are reaching a station or there is an emergency. This distance which is required is 1280 meters for a speed of 280 kilometers per hour, and for a speed of 480 kilometers per hour this is 2400 meters. So, here a comparison has been shown with respect to the speed being taken on the x axis and the propulsion efficiency which will be there when we are working with the different systems, the turbojet, the turbofan, the turbo propulsion and the linear induction motor. In the case of linear induction motor, the efficiency is constant at 100%, but in the rest of the cases you are getting the maximum value at a certain speed. Say for turbo propulsion it comes out to be somewhere around between of 320 and 640. Then if you talk about turbofan, this is coming here very nearer to 960, somewhere around 800 in this range, and in the case of turbojet it is continuously increasing. Another system which is available is known as Maglev or the magnetic levitation. Here what is being done? The passing of the superconducting magnets by figure 8 levitation coils on the side of the track induces a current in the coil and creates a magnetic field. So, if you see on the right hand side, there is this guidance system being provided on both the sides, and within that guidance system there are coils which are being used. So, there is a 8 figure coil which are used here, as well as there are propulsion coils. At the bottom this is a wheel support path. So, all of these vehicles they are going to be provided with a wheel. So, they will given the initial power, and with that initial power this vehicle will start running, and as soon as this vehicle starts running on these support systems with the pneumatic tired wheels, it will attain a particular speed. So, as soon as it attains a speed of 80 kilometers per hour, at that point, by that time all of these things get charged and the vehicle is lifted above the track by a height of 100 mm. And now the resistance which is being offered by the track is not there, it has come into the air. And these systems, the guidance systems and the propulsion systems, the guiding coils they will take it up, and the propulsion coils, now these propulsion coils they will give a force to the vehicle to move in the forward direction. So, it does not levitate unless it reaches a speed of 80 kilometers per hour. So, it is equipped with the retractable wheels, means the wheels are there, as soon as it goes into the air then wheels will go inside, the same way as it happens in the planes. Now, when one side of the train nears the side of the guideway, so this is the guideway and the train comes nearer to this, the superconducting magnet on the train induces a repulsive force from the levitation coils on the side closer to the train, and an attractive force is generated from the coils on the other side of the train, and this keeps the train in the center of the track. So, it means if it is going to the one side, the repulsive and the attractive forces are getting generated. So, if it is going to left side, there is a repulsion force getting generated here and attraction force getting generated on the right hand side, and that is how it will come back to the center. An alternating current is run through the electromagnetic coils in the guide walls of the guideway, and here you can see the assemblies. So, this is a emergency guided wheels are being provided. There are auxiliary supporting gear systems and the wheels are also there. This is a bogie frame, and within that bogie frame then there is an assembly being shown here which is a gas helium buffer tank which is used for cooling purposes, and these are the magnets. Actually these on sides the magnets are being provided. Now, the system which we are talking, this creates a magnetic field that attracts and repels the superconducting magnets on the train and propels the train in the forward direction. So, as you can see here, this is the guidance system. Within that guidance system, all of these magnets they have been provided, and these superconducting coils or magnets they are now helping to generate the speed and propelling the system forward. At the top here you can see another assembly which I was showing you in the previous diagram. This is a liquid helium tank or a nitrogen tank being provided, and it keeps it into cooling conditions. Braking is accomplished by sending an alternating current in the reverse direction. As soon as this is done, that it starts reducing the speed. The vehicle uses superconducting electric magnets which are cooled by liquid helium or liquid nitrogen. This means that once electrified, these magnets do not require additional energy. So, that is the best side of it. In the initial, up to the time when it goes to a speed of 80 kilometers per hour, it is requiring energy, but after that it is not required. Now, let us look at some of the safety features which can be provided on track. As I said, these are being taken from the features which are already being taken for the Mumbai Ahmedabad high speed rail track. So, one is a crash avoidance through DSATC, the automatic train control system. So, it has a speed check pattern. So, it will check the speed, will try to bring in the speed to the lower values. We have discussed about this device, we were talking about the various new technologies. Okay, so what it does is it helps in the form that if it is going on a track where there is a possibility of a derailment and overturning, then that will be avoided, as well as at the same time the possibility of a collision between the two trains will also be avoided. So, it helps in that two-way form. The another feature is a early earthquake detection system. So, if you see here, the corridor is going in the elevated form, and then there are certain things which are provided at certain locations. The signaling aspects or the control aspects can be there. So, if there is a possibility of an earthquake, then what it does? So, what it does is this system enables the automatic power shutdown when primary waves emerging from an earthquake epicenter are sensed. Trains will have power failure detection device which will evoke the emergency brake when the power shutdown is detected in such cases, and thus the safety of the passengers as well as the infrastructure is being maintained. Now, another thing is the continuous monitoring of the rail temperature and wind. Now, high speed rails will be fitted with a network of sensors monitoring the rail track temperature, rain monitoring. There are special sensors for that, and as well as the anemometers for the wind monitoring. Now, if you are in a high rise condition, that is elevated corridor is there and there are heavy winds which are going, then at that point of a time the operation may be a problematic condition, the safety may be hampered. So, here as soon as the crosswind speed goes above 30 meter per second, it will give an alarm signal to the operational control center so that the train can be stopped. So, these type of detection systems, they are also being provided. Then advanced loco pilot support system. You can see this is the inside of the start of the locomotive where the loco pilot is going to sit. Good number of electronic systems are being provided along with the view frames. So, the whole of the information is provided to the loco pilot at that location, which is coming electronically through the connected systems. So, there are display units, communication equipments and other tools. So, when all of the information is available to the loco pilot in the cabin, the loco pilot is able to take the informed decision. So, as per the requirement, as per the situation, the decision will be taken by the loco pilot along with in the coordination of the operational control center. Of course, the pilot has to communicate with them to finally do something on the basis of the decision being taken collectively. So, with this we close now this lecture. Here in this lecture we focusedly talked about the high speed tracks, the effects which get induced because of the higher speeds of the trains which are moving on the tracks, what can be done, what can be the possible speed values, and then we discussed about the possibilities of the modernizing the tracks, what are the various concepts which can be used to attain the high speeds, and they have been used in different countries, and then the safety features which can be taken and should be taken when these type of operations are done. Now, with this we are closing our overall discussion in this particular course. We have been discussing various aspects related to the railway tracks and the control of the trains moving on the tracks. I hope you have been able to learned many of the things in this particular course, and it has been beneficial to you and probably going to be beneficial in your further professional life. With this, my best wishes are with you, and I again convey thanks to you for taking up this course and attending these lectures. Thank you and bye. We'll meet somewhere else.